Okay, in this video we're going to be talking about the aldol reaction. So first let's really define what an aldol is. An aldol is an aldehyde and an alcohol. So it is an organic structure that contains an aldehyde, actually, or a ketone functional group, and an alcohol. So that can be a beta hydroxyketone or a beta hydroxyaldehyde, where we have our alpha carbon next to our carbonyl, and then an alcohol at our beta carbon. So we're going to be talking about the aldol reaction. This can form two products depending upon the starting materials and what conditions we use. And the difference is really whether we heat the system or not. That's really the key difference, is whether we heat our system. So you can form an aldol product, what we saw here, the beta hydroxyketone or aldehyde. That's called the aldol addition reaction, and that's the product we see here, this beta hydroxyketone or aldehyde. But we can also do a reaction called the aldol condensation, where we actually form an alpha-beta unsaturated ketone or aldehyde. So instead of having an alcohol here, we have a double bond. And the difference between these two reactions is whether we heat the system or not. So when we heat the system, that means we're doing an aldol condensation reaction and not the aldol addition. All right, so let's look at this reaction. So here you see, first we'll do the aldol addition reaction. So we're starting with an aldehyde. We're treating that aldehyde with 10% sodium hydroxide. And you don't have to list the exact amount of sodium hydroxide you're using, but I'm showing 10% just to show that this is catalytic in sodium hydroxide. You only need a little bit of the sodium hydroxide. So we'll see further examples along where I don't write 10% and I just write sodium hydroxide. So we know with this product we're going to be forming that beta hydroxyaldehyde. But let's go through the mechanism and figure out what's happening here. So the first thing I'm going to do is I'm going to draw the hydrogens in on our alpha carbon. So this dot here is our alpha carbon. There's not an alpha carbon on the left side, right? Because this is an aldehyde, so we only have one alpha carbon. So when I treat an aldehyde with sodium hydroxide can obviously act as a base or a nucleophile. And in this reaction, sodium hydroxide is going to act as a base. And what that means, it's going to deprotonate the most acidic protons, and those are the protons on the alpha carbon. So here our first step is a deprotonation step, where sodium hydroxide will remove the hydrogen on the alpha carbon. Okay, that's going to form an enolate. So let's draw in our enolate here. So now we only have one hydrogen here, and I've got a lone pair on that alpha carbon, and that alpha carbon has a minus charge. Because this is an enolate, we can draw a nice resonance structure associated with this, where this lone pair comes down to form a double bond. These electrons move up onto the O, and we have a negative charge on our oxygen. So basically, upon treatment with an aldehyde or a ketone, with base, we now form our enolate. And if we remember, we're talking about enolates. Enolates are great nucleophiles. So the question is, what is our electrophile? And in this reaction, we're going to use a second equivalent. So we'll have two equivalents of our aldehyde. Our second equivalent of the aldehyde is going to act as our electrophile. So in blue, I've drawn in my second equivalent here of the aldehyde. And now the first equivalent, the enolate, is now going to act as our nucleophile to attack the aldehyde, which will be our electrophile. So remember here is that the carbon of the carbonyl has a partial plus, and that's actually exactly where our nucleophile will attack. So I can draw the arrows from either resonance structures. I prefer to draw from this resonance structure because the bond is going to be formed from the alpha carbon. So this lone pair can come up, attack the carbon of the carbonyl, and that pushes the electrons onto the oxygen. That is our second step in the mechanism, and that is our attack step. So let's draw our intermediate here. Here's the first equivalent. Now I'm going to move that methyl group down. Here's my new bond in blue. That goes to the carbon and then the oxygen. That oxygen now has 3 lone pairs and a negative charge, and we're still connected to 2 other carbons. So we've now formed our key carbon-carbon bond here, and we now have a minus. So to satisfy that minus, if we have 10% sodium hydroxide, the rest is water. So what we can do is simply protonate that alkoxide using water. And that will complete the mechanism and complete the reaction. So there's our first equivalent in black. Second equivalent is in blue. Now we have an OH and our 2 carbons, and we have now formed our product from the aldol addition, our beta hydroxyaldehyde. So if we look at the second reaction here, the aldol condensation, what we should notice is, again, I have an aldehyde. Again, we're going to use 2 equivalents of this aldehyde. Again, we use sodium hydroxide. The only difference in this reaction is heat. So basically, when you heat this reaction up, we're going to do the aldol condensation. So let's take a look at what that product will be. Luckily for us, we're actually going to form the beta hydroxy ketone first, and then there's one additional step. What that means is the first 3 steps of the mechanism here are exactly the same. So let's redraw these. There's our H, there's our second H, here's sodium hydroxide, a lone pair is going to deprotonate the hydrogen on the alpha carbon, just as we did above. Now we only have 1 hydrogen here, and then with the alpha carbon we have our lone pair and a negative charge. This is, of course, our enolate, the same enolate we saw above. So let's draw in the other resonance structure of that enolate. Draw on our lone pair. Sorry, they're not very circular. That has a minus. Here's our double bond here. And we've now formed our enolate. Again, we're going to use our second equivalent of our aldehyde. So let's draw that in blue. Here's our second equivalent of the aldehyde. And again, we see the first equivalent is in enolate. That's our nucleophile. Our second equivalent is our electrophile. So let's draw the arrows where the lone pair comes and attacks the carbon of the carbonyl. If you wanted to draw the arrows from this resonance structure, you could draw your arrows down and then attack, but you only have to draw 1. So after our attack step, the product that we form is our first equivalent, and I usually draw those down. Here's my new bond in blue. That goes to the O minus. Still have 2 carbons attached. Just as we did above, we are now going to protonate that species using water. So let's draw that same step out here. And you see the first 3 steps are exactly the same. We form our beta hydroxy aldehyde. Now with heat, our next step occurs, and that step is basically an elimination step. To show that, we need to draw in our other hydrogen here. And we're basically going to be using our base to eliminate out OH minus. Let's make this minus a little bit bigger. So essentially what happens is when you heat this reaction, this beta hydroxy ketone will react and we do an elimination reaction. Normally, hydroxyl groups are not good leaving groups, but it does occur in this aldol reaction. So let's show the arrows. This is just like an E2 elimination. The lone pair from the O will grab that H. The carbon-hydrogen bond breaks, and that forms my double bond, which will now kick out my hydroxyl group. This is an elimination. And now what we get is there is our original aldehyde, and instead of having a single bond, we now have formed a double bond to the electrophilic carbon that has two more carbons attached. So in the aldol condensation product, instead of having a new single bond and an OH, we now have a double bond. And this is called a condensation reaction because you condense water. We're forming water in this reaction, and that's why it's called a condensation. So without heat, room temperature or below, you'll get the beta hydroxyaldehyde. But if you heat this reaction, you form the beta hydroxy, and then there's one extra step, the elimination step, to form the alkene between the nucleophilic carbon and the alpha carbon and the carbon of the carbonyl. Alright, so in the previous examples we only used one aldehyde. It's possible to do a crossed or mixed aldol, but we have to set up the conditions in the right way, and this is an example here that's not going to be effective, and I'm going to show you why. So this example is not going to be effective. Let's just put that up here immediately. And here's the problem. When I mix these two aldehydes together, one in black, one in red, with sodium hydroxide, the problem is we have two alpha carbons. So I can have the black aldehyde react as my nucleophile, but I also can have the red aldehyde react as my nucleophile. And then the other problem is we also have two electrophiles. The carbon of the carbonyl is electrophilic. So in this example here, this would not be a useful reaction because I can actually form four products. I can have the aldehyde in black act as the nucleophile and attack the aldehyde in red. I can have the aldehyde in red act as a nucleophile, attack the aldehyde in black, and then I can have the black act as a nucleophile, attack itself, and the same for the red. So let's just draw out all of the possible products here. So first let's draw the black example attacking the red example. We get our beta hydroxy ketone, 1, 2, 3, 4 carbons, 1, 2, 3, 4. Let's look at the example where we have the aldehyde in red as a nucleophile, 1, 2, 3, 4. There's my new bond to the carbon in black that acts as the electrophile. So in this case I could form these two products, but as I mentioned, the aldehyde in black could act as the nucleophile and the electrophile, so I could form that product, and the same could be said for the aldehyde in red, where it attacks itself, and we form this product. So this is not an effective reaction because I'm actually forming four products here, so it's not very useful. So what can we do to get around this problem? Well, let's take a look at a couple of crossed or mixed aldols that are effective. And here I have two examples, or actually one example. The top case we're doing the aldol addition. Because they're heat, we're doing the aldol condensation. And now these cases are a little bit different. If we look at the aldehyde in black, here I have an alpha carbon that has two hydrogens attached to it. But the key is the other aldehyde, there are no hydrogens on the alpha carbon. And we see the same thing from the bottom. It's really the same example. So in this case, the aldehyde in red can only act as the electrophile. And what that means is we can set up the reaction conditions where if I add the aldehyde in red with sodium hydroxide and add the aldehyde in black dropwise, once the enolate is formed, it will react and attack the aldehyde in red. So in this example, we're only going to get out one product, and that product would be this. Our aldehyde in black will act as our nucleophile. It will form a new bond to the aldehyde in red, which can only be the electrophile. So this would be the major product we form here. And this is a useful reaction because I only have one compound that can be the nucleophile. We would get out this beta hydroxyaldehyde in good yields. If we do the same reaction here on heat, again, it would work just as well. But in this case, if you remember, we talked about we don't get the beta hydroxy compound, we get out the alpha beta unsaturated. So what I'm doing here is there's my nucleophilic carbon, here's my electrophilic carbon, and instead of having an OH, there's a double bond. This is conjugated. And that's the product we would get from that crossed or mixed aldol. Alright, so the crossed mixed aldol reaction will only work when one of the aldehydes you add does not have any hydrogens on the alpha carbon, which is the case here. Okay, the other thing we can do is sort of another example of a crossed aldol. Here we call this a directed aldol, is where we do this stepwise. So in the previous examples we used sodium hydroxide and that reaction was in equilibrium. By using LDA, we're now doing a directed aldol. So if we work through the mechanism here, when I treat the aldehyde, my starting material, with LDA, LDA will act as a base. It will deprotonate my first aldehyde to form the enolate. So we'll draw in our one hydrogen here. Let's draw the resonance structure of this intermediate. So now we formed our enolate, and this enolate is going to sit and be stable at minus 78 degrees. So after step 1, we just form our enolate, and it sits and waits until in step 2 we add our aldehyde. So now we formed our nucleophile. Step 2 is our aldehyde, that is our electrophile, and there's no cross reactions that really can occur. So once we add in our aldehyde in step 2, that can act as our electrophile. So we can attack. Here's our first aldehyde. There's a new bond to the second aldehyde. Again, we form our O minus. And now we've really only formed one product. Then we end with a workup step, H+, so we can simply protonate that. And I guess I really shouldn't be using equilibrium arrows here. That's really one step. And again, one direct step. And let's draw in our final product here. There's the new bond we formed to the alcohol, and then we add the corresponding carbons. So in this directed aldol using LDA, there's only one possible product that we can form. our beta hydroxyaldehyde. And this is a very good way of having two different aldehydes react. If I switch this, where I started with the aldehyde in red, and that would be the nucleophilic aldehyde, and the aldehyde in black was over here for step 2, we would get out a different product. Okay, so for class, what I want you to do is to draw out the mechanism for both of these reactions, and then obviously draw the final product. So in this case, we have an aldehyde treating it with sodium hydroxide. If you notice, there's no heat, so we're going to get the beta hydroxyaldehyde as our product here. In the second example, we're doing a mixed aldehyde with sodium hydroxide and heat. So now we would have our alpha-beta unsaturated compound. And what you'll notice here is this aldehyde does not have any hydrogens on the alpha carbon. So this aldehyde has to act as our electrophile, which means that aldehyde acts as our nucleophile. So for class, if you can draw the final product and draw the mechanism to form it for the first example, and for the second example, please draw the final product and the mechanism of how that's formed as well.